Okay, in this problem we are told that a baseball is hit giving it a resultant velocity of 53 meters per second at an angle of 38 degrees above the horizon. And it lands in the stands at the same height it was hit. In other words, we don't need to worry about calculating for the difference in height. It lands at the very same vertical displacement that it was hit at. So we're going to assume that this is a level launch. Right off the bat, if it's telling me that my resultant velocity is 53 meters per second, I'm going to label this. You need to draw a picture. This picture was already drawn, obviously, but you need to draw a picture. And it's hit at an angle of 38 degrees above the horizontal. It wants to know how long the ball was in the air for. Well, before I do anything, the very first thing that I need to do is break this resultant up into its components. In this case, I want to find the velocity in the horizontal direction and the velocity initial in the vertical direction. Because keep in mind, this initial component is going to slowly get to 0 up here at the top, and then it will continue to increase in magnitude, but just in the opposite direction until it hits the ground at the same height. So I'd want to break those things down. Let me make my menu of stuff. Remember, the menu is important. You fill it out, and it helps you keep track of the things you know and the things that you are looking for. So in this case, I will want to find my horizontal velocity and my initial vertical velocity. I'd also want to find perhaps my horizontal displacement and my final velocity in the vertical direction, in addition to my vertical displacement, in addition to my vertical acceleration, and of course, don't forget, time is key. If you can find the time that this ball is in the air, you're going to crack the case wide open. Okay, so the first step to breaking down a resultant vector into its components, if you remember from the previous unit, is to, well, we're given a vector that looks like that, and here are the components. We will draw them so we can try to visualize them. You know, here's the thing with resultant velocities in these two-dimensional problems. Once we break them up into their components, you're almost never going to see them again. We're only going to look at this either in the horizontal or in the vertical direction, and until maybe the very end, we will not look at this resultant velocity again. And of course, we have an angle of 18 degrees. So to solve for these components, if you look on the back of your reference table, it says that the horizontal component, when the angle is between the horizontal and the resultant, the x component is the resultant times the cosine of the angle between them, and the initial vertical component will be the resultant times the sine of the angle between them. If you were to work these out, plugging in 53 meters per second for the resultant of each one, and 18 degrees for the angle of each one, then you should find that the horizontal velocity is going to be 41.8 meters per second. Make sure you show your units in this menu. And similarly, if you were to solve for the vertical component, you should see that it is 32.6 meters per second initially. So that was a very big, important step. We can't do it without finding those components, because we can't look in just the x and just the y unless we know what those values are in just the x and just the y. Okay, let's get back to this problem. It wants to know how long is the ball in the air. In other words, it wants to know the total time that this ball is in the air. Well, this is a key part for you to realize. If we're talking about how long the ball's in the air, we're talking about the vertical stuff, because it is really this guy here who's responsible for how long I'm going to be in the air. This guy is more responsible for how far downfield I'm going to be, but this guy is most definitely responsible for how long I'm going to be in the air. So I'd like to be able to solve for this information. Realize that this initial velocity, if it starts out at 32.6, it will eventually get smaller and smaller and smaller until it's 0, and then it will get larger and larger and larger and larger until it's back to the same magnitude but just in the opposite direction. The fact that I'm moving vertically up and vertically down immediately tells me, alright, I gotta call some direction positive and I gotta call some direction negative. Meaning if anything is pointing down, I'm going to call it negative. If anything is pointing up, I'm going to have to call it positive. So to finish my menu, if I realize that I will return to ground at the same level with the same magnitude of velocity but just opposite direction, then it is implied, this is an important step, it's implied that the final velocity, if I land at the same height, and only if I land at the same height, is the same magnitude but just opposite in direction. I do not know the vertical component of the height, but I do know that the acceleration due to gravity is 9.8 meters per second squared downward, or in this case, as I've labeled, negative. And I'm trying to find the total time. Well, hopefully I have enough information. Over here I have the initial velocity, the final velocity, the acceleration, and I'm looking for the time. If you look at the back of your reference table long enough, you should see this equation. The final velocity is equal to the initial velocity plus the acceleration times the time. I'm trying to get this guy all alone in a room by itself. Now, because the acceleration is being multiplied by the time, I can't just divide that out first. I also have this guy over here which is being added, so make sure you get your order of operations. To get that t all alone, I must first subtract the initial velocity from both sides, and then I can divide the acceleration from both sides so that I can get time all alone. If you did your algebra correctly, you should have something that looks like this. The final velocity minus the initial divided by the acceleration is equal to the time, or in this case, a negative 32.6 meters per second minus 32.6 meters per second divided by an acceleration of negative 9.8 meters per second squared. If I run these numbers through my calculator, I end up getting a negative 65.2 divided by a negative 9.8, which gives me a total time that this ball is in the air of 6.65 seconds. Okay, now the second part of this question, it wants to know what is the maximum height above the ground that the ball will reach. Again, if we're trying to find the maximum height, we're talking about something in the vertical direction that's going to affect this. We're trying to find this, the distance in the y direction. There's a big important thing that you need to realize here. It's that the maximum height in the vertical direction only occurs halfway through the trip if you start and end at level ground at time equals half. Now, this isn't the case for objects where you launch them at an angle off of some height above the ground like this. It turns out time halfway is not the time where the highest displacement above the ground is, but for this problem where we are on level ground, you need to realize that the maximum displacement occurs when it is at the halfway point. So if that's the case, my maximum displacement occurs at half the time, or in this case at 3.325 seconds, which is half of 6.65. So if that's the case, what I want to do is I want to find the displacement at that time. Our old friend, displacement is equal to the initial velocity times the time plus 1/2 the acceleration times the time squared is back to help us out. But in this case, please don't make this mistake. Do not just assume that this initial velocity is always going to go away to 0, because in this case it's not. Our initial velocity is not 0, it's something. In this case it's 32.6 meters per second. And also notice that I'm putting these little subscripts to remind you that this is all stuff that happens in the vertical direction. If this were in the horizontal direction, I would not have this term because it does not accelerate. But it isn't in the horizontal direction, so I'm going to keep those terms for acceleration. Okay, I gotta ask myself, do I know enough information here? Do I know the initial velocity and the y? Yes. Do I know the time? Yes, but I need to remind myself it's not the total time, it's only the time halfway, that is, to that point right there. But I do know it, and I also know the acceleration due to gravity, and again, I know the time. So to solve this problem, it becomes as simple as throwing in the numbers and solving. My initial velocity in the vertical direction is 32.6 meters per second, multiplied by this time halfway, which is 3.325 seconds, plus 1/2 of a negative, don't forget the negative because the acceleration due to gravity is pointing down, 9.8 meters per second squared, times 3.325 seconds. Don't forget to square this term as well. Oh boy. Okay. If you take all of this, you should get that it is 108.4 meters. And if you take all of this, you should get that it is a negative 54.2 meters. And 108.4 meters minus 54.2 meters should give you the displacement in the vertical direction of 54.2 meters, coincidentally. So now I have solved for this value above the vertical. Okay, now that was a lot. This last question, thankfully, is not nearly as involved. It simply wants to know how far away from home plate does the baseball land. Now, after all this, I really do hope that you realize this is kind of a walk in the park. If you want to know how far away from home plate, it's talking about the horizontal displacement. I have pretty much solved for everything on this menu except for this guy. At this point, you should realize that because the velocity in the horizontal direction stays constant, I can use this equation to solve for the displacement. I know time total. Again, we're back to total time because it's this entire trip. And I also happen to know the velocity in the horizontal direction, and I know that it is not going to change. It will stay the same the entire way because we are neglecting air resistance for this ball. At this point, to get the displacement all alone, I'm going to multiply both sides by time. That cancels out. And now I have the total time, 6.65 seconds, multiplied by the velocity in the horizontal direction, 41.8 meters per second, and I get 278 meters, or 278 meters away from home plate.